You're already taking a picture, Leah. There's nothing here. Right?
But that one is dry. You already finished writing that.
Yeah. Now he's following you. Where are the organizers? Oh, hi.
I'm delaying things by 5 minutes to Alex's thing started 5 minutes later.
Oh, okay. Sounds good. Okay.
I'll introduce you. I didn't mean to.
Oh no, I was being facetious because I'm an organizer. So I was gonna say like, where's the organizer? So that's all.
Friday. Well, okay. It was funnier that you weren't for my Friday lecture in week 1 because none of the organizers, none of the higher up people were there. So I chaired my own. It was great. Whatever time. Yeah. Right. No,
Yeah.
Okay. I'll sorry. What's the title again?
Oh, Eigenstate order.
Okay. Great. Okay. Let's get started. So this morning and afternoon, we have 2 research seminars given by Vedika Khemani. And just to introduce Vedika, she's one of the organizers who
Thanks to the organizers for inviting me or burdening me with this. Yeah.
And Vedika will be talking first about eigenstate order today.
Okay, thanks. All right, so I was supposed to be giving a seminar at the end of each of the first 3 weeks, appropriate to the topics of the week, and it kept getting bumped. So now I'm giving 2 seminars appropriate to the first week and the second week. The third week, unfortunately, I won't be able to talk about, but since someone asked, what's next with these quantum LDPC codes, I think from the physics point of view, there's actually really exciting things to be done in terms of understanding the physics of these codes understanding the physics of these codes rather than the computer science of these codes, and also in taking some of these constructions these product constructions that Alex listed and using those to construct interesting physics models. So this is something that I'm working on, and I won't get to tell you about it, but hopefully there'll be some papers on this in the next month. Okay, so for my first lecture, let's go back to week 1, and also let's go back in time, 10 years, okay? So this is going to end with an experiment that's fairly recent, but this is not kind of bleeding edge stuff. We're going back to week 1 and 10 years in time. And, a focus of the school, this Boulder Summer School, has been phases of many-body quantum dynamics, right? And we just launched into talking about phases of monitored dynamics, dynamical codes, all of these things as if it was completely natural. And indeed, by now it is. But 10 years ago, this was still really not something that was mainstream to talk about. If you were thinking of a many-body, strongly interacting quantum system, and you were asking about the dynamics of such a system, the prevailing kind of assumption was that, well, this was just going to reach some boring or possibly interesting thermal equilibrium state, but the interesting features would be in the properties of that equilibrium state or in the properties of the ground state. But the approach to that equilibrium, the dynamics of the system, were just going to be messy and non-universal. Okay, but remarkably, we've, of course, come to know and appreciate that this is not the full story. There's a lot of rich universality in the dynamics of many quantum systems. And there's lots of different ways to distinguish these dynamical regimes. starting from the basic question of whether the dynamics of a many-body quantum system can bring the system to local thermal equilibrium on some accessible timescale. Okay, so this is the topic of thermalization, many-body localization, pre-thermalization, scar dynamics, which you heard about in week 1. This then naturally leads to the question of how do we define phases for systems that do not reach thermal equilibrium. Okay, all of our understanding of phases of matter is based on the framework of equilibrium thermodynamics, where you look at a ground state or a Gibbs state and you ask about the possible orders. But when systems do not reach thermal equilibrium, so that these descriptions are not even a good starting point, how do you talk about phases in that setting? Conversely, even when systems do reach thermal equilibrium, is there interesting universality in the dynamics of how they approach thermal equilibrium? Okay, so this could be the dynamics of entanglement growth, the dynamics of spreading. How do we discuss universal features of such dynamics? And by universal here, I mean things that do not care about the microscopic details in the system. Okay, so the work on random that you heard so much about, those models were constructed as a way to talk about, universal features that only depend on locality and unitarity, but may not care about the microscopic details of individual Hamiltonians. Okay, of course, now we've moved past even talking about Hamiltonians to directly talking about universality and dynamical phases without Hamiltonians and even without unitarity. Okay, much of week 3 or week 2 was spent on phases of monitored dynamics. These are circuits with unitary gates, with measurements. We don't even have unitary time evolution. And we saw that to talk about and even define phases in this setting led to this very, very deep convergence between ideas in many-body physics that we're talking about phases in the first place, and ideas in quantum information about how systems retain quantum information, how they encode quantum information, how an observer learns something about the system by making measurements. So there's really, I think this body of work has led to a very, very deep convergence in the fields of quantum information and many-body physics. And that, in my view, recently has led to this very exciting topic on dynamical codes, also known as Floquet, or as of yesterday's archive posting, dynamical automorphism codes. So, these are codes in which the quantum information, the encoding of quantum information, intrinsically relies on some kind of dynamical cycle. Okay, so again, dynamics and these questions of time are also entering in very intrinsic ways to generate or to produce new paradigms for quantum error correction. And in trying to understand these dynamical codes, I think there's a lot of work to be done in, again, thinking about the physics of these codes. But something that is becoming apparent is that really to understand these, you have to think of some non-trivial cycle in a space of codes that your evolution is taking you through. And indeed, when in the work that we have done and understand in thinking about phases of unitary Floquet systems, I'll tell you a little bit about this today. It again becomes important to think about non-trivial cycles. Okay, you can't understand the properties of the unitary Floquet evolution by looking at individual points along the evolution, but you really have to think of the cycle, the whole. And that same idea, I think, is appearing in a very intrinsic way in this body of work. Okay, so I'm going to start by telling you about this concept called eigenstate order. This is a framework to define in a concrete way phase structure in an out of equilibrium setting where you don't have ground states, you don't have equilibrium states, time-independent Hamiltonians are not necessary, okay? I'll show you how this framework allows you to get forbidden orders, orders that you would have thought are not allowed by the laws of thermodynamics. And these orders have measurable dynamical signatures that I'll talk about. But I think, to connect with the themes that we've talked about in this school, while the specific structure that I'll tell you on eigenstate order is something that we discuss for eigenstates of localized systems, you'll see that the ideas actually have found much broader applicability, for instance, in thinking about monitored or measurement only dynamics that are enriched with symmetries. You get much of the same type of physics entering in. or at least conceptually the same types of physics. And then also some connections with these dynamical codes, okay, which will be more apparent when I talk about eigenstate order in flow case systems. And then I'll end with some recent experiments. Okay. So to discuss eigenstate order, let's start with the simplest Hamiltonian that we can write down, which is the 1D transist field Ising model. As an organizer, I told some of our speakers that they didn't need to introduce the toric code, but now I'm going to spend 5 minutes introducing the 1D transist field Ising model. So forgive me for that. Okay. Okay, so that's your Hamiltonian. You can write down a phase diagram for this Hamiltonian as a function of temperature, J minus H. This has a ferromagnetic phase, and at any finite temperature, this model is a pyromagnet, and that is Peierls' theorem that a 1D short-range system cannot show any type of ordering at any finite temperature, okay? At H equals, this model has Ising symmetry, which is flipping all the spins in the X basis, okay? So HP is 0, and strictly at H equals 0, so for zero transist field, we have two Ising symmetric ground states, which are exactly degenerate, which look like Schrodinger cat states of this form. Okay, so you have the all up state and the all down state. If I only had the all up state, that would not respect the Ising symmetry. That's a symmetry broken state. So your symmetric ground states, which are exactly degenerate at H equals 0, look like these Schrodinger cat states of up and down with this plus or minus cat. And of course, these are also eigenstates of the Ising symmetry with that same sign. Okay. The excited states can be ordered. Again, I'm going to work with symmetric states. The excited states can be ordered by counting the number of domain walls. Okay, so again, I'm at H equals 0 here. So for your first excited states, and let me just do OVCs. So my first excited states will look like states where I have one domain wall, right? So that's the flipped version. Yeah, yep, that's right. So I have one domain wall somewhere, but then this domain wall can be anywhere in the system, and it will incur the same energy cost. Okay, so I have one state that looks like this, I have another state that looks like this, and have another state with the domain wall moved over, but all of these states have exactly the same energy, which is energy J, okay, corresponding to that one single domain wall. And likewise, I can have the second excited manifold, where now I have L choose two states. Okay, so here I have L states, depending on where I want to put my domain wall. Here I have L choose two states with two domain walls somewhere in the system. Okay, and again, they're Ising symmetric partners and so on. Okay, so all of these are degenerate. And my spectrum looks like the spectrum looks like a pair of degenerate ground states, the plus cat and the minus cat. Then you have L first excited states, you have L choose two second excited states, and so on. And you build up your entire many body spectrum. And the only thing your energy cares about is how many domain walls are. Okay, now you turn on a small h, okay? And what the h does is it flips spins, and by flipping spins, it hops domain walls, right? So for instance, if you had a configuration with a domain wall here, which looked like that, and if I flip this spin, then this domain wall hops. I have, okay? So by adding the transist field, I give dynamics to my domain walls. And that means that these previously degenerate states, which had just one domain wall in one location, of course, because it was degenerate, I could have picked any basis to write them in. But as soon as I add a small h, that degeneracy gets lifted because your domain walls are now free to hop. So they delocalize within the degenerate manifolds, and they also couple the one degenerate manifold to another, and it causes some splitting in the ground state degeneracy, which now goes as delta E, which is exponential or in system size, okay? Because by acting with this transist field or order L times, you can take one of the all up state to the all down state, and that higher order process gives you this exponential energy splitting. Okay, so this already means that because of this tunneling, right, your eigenstates at finite temperature have fluctuating domain walls, okay? And this is why order is destroyed in 1D, because in one dimension, the entropic gain that you get from these fluctuating domain walls beats the energy cost of creating those domain walls. So then, just at a finite energy, you can create two domain walls. They can fluctuate everywhere in the system. And now you go in and you measure some spin-spin correlation function, and you get zero, okay? So your eigenstates then look like, instead of looking like this, now your eigenstates will have, you'll still have your two almost degenerate ground states, but now your excited states will be superpositions with, domain wall at position X, sum of all X, things like that, okay? Some coefficients here. To diagnose the spontaneous symmetry breaking order, of course, I have to measure something like a correlation function. System size goes to infinity, R goes to infinity, and I want this to be non-zero, and I can measure a connected correlation function. So as long as I have a cat state and I'm measuring this at zero temperature, so at zero temperature, if you have a cat state, then you can see that this is non-zero. But as soon as you have these fluctuating domain walls, because when you measure this correlation function, you're going to be crossing either an odd or an even number of domain walls, you're going to get zero, okay? Good. And just as a aside, as long as I'm at any finite system size, measuring just a single magnetization operator is zero in any eigenstate because of the Ising symmetry. Okay, every eigenstate is an eigenstate of the symmetry. So if you measure a symmetry broken operator, you get zero. Okay, good. Now let's add disorder. Okay, so if I add disorder, my Hamiltonian now becomes Ji Zi plus 1 plus Hi Xi. And these are going to be drawn from some IID distributions with some mean and some variance. And let's consider, again, to be in the regime that's analogous to the ferromagnet, let's work in the limit where the mean value of J is bigger than the mean value of H, okay? So your Ising interactions are dominant. And immediately adding disorder does one important thing, which is that it lifts the degeneracy between all those previously degenerate manifolds that we had. Okay, so previously, any state with one domain wall had exactly the same energy as any other state. Now, because this Ji depends on which bond, a domain wall on this bond costs very different energy from a domain wall on that bond, and so on. Okay, so when you start trying to hop the domain walls by turning on H, you might find that this is off resonant. Okay, so if the difference in energy between having a domain wall here and a domain wall here is large, that's said by some disorder scale W, then if you try to hop these domain walls at a scale set by H, if H is much, much less than W, then this hopping is very off resonant and your domain wall gets stuck. Okay, and that's of course this the picture of Anderson localization, which I assume David mentioned in some form or another. Okay, this transist field Ising model is actually exactly it's a free fermion model. If you do a Jordan-Wigner transformation, this is a Majorana, free Majorana chain. Okay, so if you have a non-interacting model in one dimension with any amount of disorder, you know that the system is Anderson localized, which means that all excitations in your system get stuck. In this case, in this regime, the excitations are domain walls and they're going to be stuck, okay? In the opposite regime, in the paramagnet, your excitations are just spin flips in the sigma X basis. And again, instead of being delocalized, you're going to be stuck, okay? So now, yeah. Sorry? Weak localization is about interference. For strong localization, divergent expansion, you have to worry about resonances, but that's okay. Yeah. Correct. Yeah, because now my particles are my domain walls and my H is causing the hopping. Sure, H is disorder. You can have disorder in both. Sure, I mean, but I can look at it in the paramagnet, and then my H is going to be my particle, and J is going to cause the hopping. So I wanted to work on both sides, but it's a 1D disordered model, short range, so it's going to be Anderson localized. Yeah. Whatever the excitations are, they're domain walls on the ferromagnet-like side, and they're spin flips here. Exactly. So when when in the opposite limit, when H is much, much bigger than J, then my eigenstates will look like that, like in the sigma X basis. And this is now the excitation, the spin flip, and that's going to be localized. Okay. Yeah. Can't hear you, sorry. So the question is the assumption that the disorders mean zero? It's not necessary. It can have any mean. Then you would look at some squared, you would look at some RMS value of the disorder. Yeah. Right. Yeah, because even if it's centered about some mean, which is zero, like, so suppose that's what your distribution of J's looks like, and some very wide distribution with mean zero. On one bond, your J could be somewhere there. On another bond, your J could be that. So you could have some J, which was, if I'm again plotting it like a potential for domain walls, I could have some J which was high, like, some J which was very high, some J which was very low. And the only difference is like, what's the spread in J's and how does that compare to the hopping? Okay. There's another question somewhere here. Okay. It's going to turn out to not be important where there's only going to be one feature that's important. I'll draw the phase diagram. But yeah, I mean, if you, yes. Exactly. So I'm going to get to that. Yeah, exactly. So that's why, that's why I put disorder in both, because I'm going to talk about localized phases in both these limits. Okay. So I'll just draw this and then we can unpack it. So you can draw it like some average J minus average H or RMS. I mean, in these problems, it's often pretty common to take log normal distributed disorders, and then you can have the means be non-zero. So that's fine. So now at any energy density, okay, and I'm going to talk about energy density rather than temperature, because in a localized system, temperature doesn't mean anything. The system doesn't reach thermal equilibrium. So all you can talk about is the energy density. And at every energy density, this regime where J is dominant is a spin glass rather than a ferromagnet. Again, and explain what this means. And here it's a paramagnet. Okay, and both of these regimes are localized. Okay, and then this critical point, this critical line, this is an infinite randomness. This is infinite randomness criticality. Daniel Fisher solved this problem for the ground state in, I don't know, I think 95. But you can show that the math is actually identical. Whatever Daniel did at zero temperature in this non-interacting problem, it's true at every energy density. Okay, so this whole line has exactly the same criticality, which is this infinite randomness criticality, and you go from spin glass to paramagnet. Okay, and now let me just talk briefly about what these eigenstates look like in these two limits. So again, let's start with some dominant J interactions. In fact, I can even turn this to 0 for now. Okay, and now your eigenstates, I'm going to use n because this can be the nth eigenstate, is again going to have some Ising even or odd symmetry. It's going to be Ising even or Ising odd. And this is going to be just some random pattern of domain walls and its Ising reversed partner. Okay, I guess I didn't draw a very random pattern. Fine. Okay, whatever, right? So when H is 0, your eigenstates strictly look like this. Previously, you had a choice, okay? This was one basis for a whole degenerate manifold of eigenstates. Now you have no choice. Your degeneracy has been exactly broken. So you have a bunch of states in the Ising even sector, each of which look like these states which are stuck. And then you have their Ising paired partners in the odd sector. Okay, and that's the plus and the minus. And there are 2 to the L such states. So this many body bandwidth is order L. This energy spacing is exponentially small in system size. It's e to the minus L, which means that states that are very, very close in energy are actually very different configurationally. Okay, because if you come in and you flip one spin, okay, that costs an energy corresponding to, you've changed the energy of one domain wall or 2 domain walls. But that's an order 1 energy, it's some large order 1 energy. So, you have to go if you want to go this order W, this disorder strength away, that corresponds to like 1 or 2 spin flips, then you've actually traversed kind of exponentially many states in the middle of the spectrum. Okay, so this is this business that people refer to in MBL or localization called the mobility gap, which is that, you act with some local perturbation to your Hamiltonian, and you're going to want to try to connect to things which are nearby in energy, but things that are nearby in energy are actually very, very different in configuration space, so you can't connect to it at any low order. Yeah. This is the whole spectrum. I'm saying every eigenstate, this is just an eigenstate index. Every eigenstate just looks like some frozen configuration of domain walls with Ising symmetry. Okay, so it has the Ising even, the Ising odd. And if you turn on some small h, because your quasi-particles are localized, I'll just replace this equal sign with a sim sign, which means that I'll pick up some weak dressing. Because energy is extensive. It's just a total. I mean, all your states have to fit within an energy which can't be larger than L. Yeah. Exactly. Yeah. Okay. Good. So what I've done so far is to tell you that if I go in, so each eigenstate, right? So each eigenstate at h equals 0, this is exact. At h not equal to 0, I'll modify this in a moment. Each eigenstate is labeled by their eigenvalues under this set of stabilizers, zi plus 1, and the Ising reversed, and the Ising symmetry. Okay, because they're all cat states, and this tells you where the domain walls in your cat states are. Now, if you go in and you measure your spin-spin correlation function, okay, in a given eigenstate, this is a frozen long-range ordered state. Okay, this is not a thermal state which has all this order washed out because of superpositions and fluctuations. In this state, if you measure some ZZ correlation function, so suppose that's X and that's X plus R, okay, you're just going to count how many domain walls did you cross in measuring this correlation function. If you crossed an even number of domain walls, you'll get +1. If you crossed an odd number of domain walls, you'll get -1. Okay, so this is equal to +1 or -1, depending on number of domain walls between X and R in state psi n. Okay, so if I go in and measure this correlation function in every one of these eigenstates, I'm going to get +1, -1, +1, and so on. But if I average over all of those states, like I would do in a thermal average, if I look at trace of e to the minus beta h, or beta en psi n zz psi n, then that is 0, okay, because of this fluctuating sign. But notice that this is a very different kind of 0 than the 0 you would get in systems that obey the eigenstate thermalization hypothesis, because in systems that obey the ETH, this thermal average has to agree with the quantity you would compute in a given eigenstate. Okay, so in that case, you would compute this correlation function in an eigenstate. Because of these fluctuating domain walls, that single eigenstate would give you something that's 0. But localized systems, because they're defined by their eigenvalues under all of these different local constants of motion, they do not obey the eigenstate thermalization hypothesis. So if you plot this correlation function, Cn, as a function of the eigenstate number n, you would get a bunch of things that look like +1 and a bunch of things that look like -1, whereas the thermal answer would basically be, 0, except maybe at low temperatures, at the edges of the many body spectrum. Okay. Any questions?
But I guess any sort of window that you grab, just one exact eigenstate, you have tons of different.
Yes, absolutely. You average over any finite energy window, and you're right. The order, the signature is washed out. Okay, good. So if you do want to do averaging over energy windows, yeah, Victor, what happened to it? It's illegal to write on cat states? I don't. That's right. But at any finite system, your eigenstates are symmetric states. So that you can do one of two things to talk about symmetry breaking. You can either measure 2-point correlation functions. Okay, and this is in connected 2-point correlation functions in a symmetric state. So you can do that at any finite system size, and then you can take the limit of the system size going to infinity and the separation x going to infinity, or you can add a small symmetry breaking field which collapses your cat state. You can measure the magnetization in that collapsed cat state, but then you need to take the limit of the system size going to infinity, and then the limit of your the longitudinal field going to 0. Yes, I mean, okay, so if I'm talking about the eigenstates of finite systems, which are then going to approach a large system limit, I have to work with cat states. But once I have approached that limit, if you're going to talk about physically realizable initial states, then those are going to be symmetry broken. Yeah, but there's going to be signatures of this even in those symmetry broken states. What? I mean, that's what you would do in the cat state. You have to measure a 2-point correlation function. If you measure a 1-point correlation function in a cat state, you get 0 because PZP is minus Z and P psi is plus or minus psi. So if you start in an eigenstate of the Ising symmetry and you measure just the magnetization, you get 0. That's why you measure a 2-point function in a symmetric eigenstate, or you measure a 1-point function with a small symmetry breaking field. But this is the standard of what you would do. Yeah. Okay. Yeah, these are your conserved integrals of motion. That's right. Yeah. So at h equals 0, it's these, and at h away from 0, they're going to get dressed a little bit. I'll come to that. Okay. So someone asked, if you take an average over a small window of energies, what happens? Well, if you take an average over a small window of energies, because of those fluctuating signs, your signal does wash out. So instead, and this should remind you to a lot of the lectures in week 2 on measurement-induced phenomena, you need to take a nonlinear average. So you need to compute something like a square, okay? So if you do e to the minus beta en, so if you want to look at some squared, this is just some observable here, okay? You want to look at the square of that overall eigenstates, okay? And that's now going to be not equal to 0. And if I measure this, if I do ZZ for this in this spin glass phase, everywhere in the spin glass phase, I'll get something non-zero. So this should very much remind you now, okay? So there's been this body of work that many of you in the audience have been involved in phases of, monitored dynamics with symmetries. Okay, and you may have even talked about spin glass phases and paramagnetic phases and so on, but the terminology is coming exactly from this type of work, because you can see that if I turn my H off to 0, then every single eigenstate is labeled by its eigenvalues of the stabilizer Zi plus 1 and the Ising symmetry, okay? And in monitored dynamics, with these Z2 symmetries, what you can do is you can start with an Ising even product state, which is plus X everywhere. And then you can go in and randomly measure these ZZ stabilizers. All of them commute with the Ising state that you started with. So you're not going to change that quantum number. But then you're going to pick out, by doing those measurements, you're going to pick out some trajectory. And that trajectory that you pick out is exactly one of the eigenstates of this disordered Ising model at H equals 0, okay? And now if you go in and you compute something like a ZZ correlation function, if you compute it in that trajectory, you'll get +1 or -1. But if you average over all trajectories, which we've been hearing a lot about how that's illegal to do, then that order washes out, okay? Unless you compute some nonlinear function. Exactly. Because in this monitoring, you're just going in and measuring these stabilizers. Because you started in the plus X state, you can get any of those outcomes with, you can get +1 or -1 with equal likelihood. So, by picking out a trajectory, you got +1, -1, -1, whatever. You picked it out on every single bond, and then you've uniquely gotten a cat state with frozen domains. Okay, and in the monitored dynamics, you can now start interspersing your ZZ measurements with some X measurements, and then drive a phase transition. But that phase transition also takes you from a spin glass to a paramagnet as those relative ratios are tuned, but that criticality is different from the infinite randomness criticality. Yeah.
Yeah, maybe I'll do there's also two phrases next to this point.
I don't want to get into Griffith's physics right now, because that's a different thing. Okay, yes.
Very generalistic, but we understand that in higher dimension there is there's a finite
Yeah.
beyond it. So can we see this like where this maybe the weak fails like in some higher dimension?
Good. Yes, let me come to that in a moment. Yeah.
Is this detectable with some like 4-point function, like equally spaced?
You don't need to do that. Okay, so we'll talk about dressing in a moment. So with monitor dynamics, we talked about how this was really hard to see. My second lecture is actually going to be about how you can, experimentally, yes, it doesn't scale up, but you can actually go very far. But if I'm just talking about now Hamiltonian eigenstates, okay, which are, you can see this kind of conceptual similarity with these quantum trajectories in this measurement only dynamics, but because I'm talking about Hamiltonian eigenstates and this kind of function, this actually is observable, okay? So you can compute this just by looking at dynamical two-point correlation functions in time, okay? So if I look at sum over n, sum over eigenstates, O of t, O of 0, n. Okay, so now I'm asking the question of, you can take any initial state, you can expand it in a basis of eigenstate. Maybe that'll give you some coefficients here. Heck, this could even be a thermally averaged dynamical correlation function. But if you look at this two-point correlator, which asks about memory, okay, memory in time now, then you can insert a complete set of eigenstates here. Okay. And this expression now reduces to sum over nm, O nm absolute value squared, e to the minus I, en minus emt, e to the minus beta en. And at late times, these energy differences dephase, okay? So you end up going to the diagonal ensemble. The fact that you go to the diagonal ensemble just relies on not having degeneracies in your energy spectrum, and that has nothing to do with thermalization. So by the time you've gone to the diagonal ensemble, you get exactly the correlator we were after, which is NON squared, okay? And this is the reason that this kind of physics, the spin glass physics, is actually observable in the dynamics of your system, because you just have to measure these 2-point correlation functions. And in fact, these 2-point correlation functions can be averaged across the entire spectrum. That's the key signature of eigenstate order, that it's not something that just lives in a vanishing part of the spectrum, but it's really something that you want to probe across the entire spectrum. Yeah. Formally, you do. So formally, you have to take t to infinity, but in practice, you never have to wait that long. Things dephase much faster. Yeah, yeah. So this is the Edwards-Anderson spin glass autoparameter, and it's probing a memory in time and relating that memory in time to a feature of long-range order in the states, but that feature is glassy because these signs are random, okay? So just because you average in C0, that doesn't mean there's no order in the spectrum, okay? So now let me briefly just mention the toric code, and then I'll come back to the question of dressing and L-bits, okay? Okay, so if you're good, so Victor in his lectures, was talking about all these different subspaces of the codes, and one of the subspaces was defined by the +1 eigenstate of all the stabilizers. But he pointed out how you can equally well take subspaces where some of those stabilizers are -1. Okay, so indeed, again, if you're thinking about something like a toric code, I can add here some disorder in the stars and some disorder in the plaquettes, okay? And now my entire spectrum, once again, before I add in any perturbations or hopping, is going to be labeled by these eigenvalues of AS, BP, and then the Wilson loops that define the topological sectors, okay? So that means that if I compute some Wilson loop to diagnose topological order, in an ordered phase, this is a perimeter law. In a disordered phase, it's an area law. So this is going to be the product of all the P's, product of all the plaquettes, ZZ plaquettes in that loop. And once again, depending on the signs in that configuration, right? Because every configuration, every eigenstate is just frozen star and plaquette defects. So depending on which configuration I pick out, I could get some kind of negative sign, negative signs. But again, this will be either +1 or -1, but not 0, unless you average. Okay, and then you could go in and you can perturb the toric code model by adding in things that give you, that make BP violations and things that make AS violations. These are these errors that we've been talking about. And once again, up to some very, very long time scales, if you're sufficiently disordered, you expect that this type of freezing will survive. Okay, good. So let me now briefly talk about dressing, which someone asked about. Okay, so coming back to the disordered transverse field Ising model, Ji plus 1 plus Hi xi. Okay, so the commuting stabilizer, the commuting projector limit of this that we've been discussing is Hi equals 0. Then you know exactly what the spectrum is. You have an extensive set of okay, bigger, extensive set of L bits, which are local integrals of motion. Okay, so this model is integrable. Every eigenstate can be labeled by its eigenvalues under Ci plus 1, this global parity symmetry. Okay, now you add in a small h. Because this is just an Anderson localized system, there's a local unitary transformation that takes you from your old quasi-particles, which are strictly localized on one side, to slightly smeared out quasi-particles, which are now these dressed operators. Okay, so if you had a spin that was strictly on one side, with some local dressing, it'll pick up some weight a little bit further out, but this envelope is exponentially decaying with some localization length. Okay, so there exists some finite depth unitary that converts this Hamiltonian into a purely diagonal Hamiltonian written in terms of these tau I, tau j operators, okay, which also has Ising symmetry in this case. And these tau I operators are basically going to be some locally dressed, this is local, some locally dressed versions of your sigma operators, okay? And so far, I'm only talking about Anderson localization, so everything is exact, okay? This was, someone asked, what about Anderson localization in higher dimensions? I'm always working in this strong localization limit because I have my disorder strength be the largest scale in the problem. So even if you're in higher dimensions, as long as there's a strong localized regime, you're fine, okay? You're gonna get these dressed operators. The way I construct these dressed operators is actually this matrix, I won't get straight whether it's U or U dagger, it's one of them, has every one of your actual many body eigenstates in its columns, but there's a huge, yeah, Victor. Sure. So in for 1D Ising, these are exactly your free fermion quasi-particles. They're not non-local when you're localized. They're not non-local, they're exponentially localized. But you're going to be, the quasi-particles are local in the Jordan-Wigner basis because the quasi-particles are ZZ, they're not Z. If you had a single Z, you would have a Jordan-Wigner string. With ZZ, you have a local fermionic operator. And that local fermionic operator, which was, it wouldn't have been the eigenstate without disorder, but it was a valid quasi-particle with the disorder, and that just gets locally dressed. The operators are local. The diagonal, the Jordan-Wigner transformation is non-local, but your quasi-particles, you'll construct your many body states by acting with some creation operators, right? And these, but this is a many body eigenstate. And this creation operator is going to be, because I'm not talking about, there's no momentum conservation or any of that. This creation operator is going to be some dressed version of your bare creation operators. And this dressing is going to be exponential. It is. So that's the conjecture with MBL. Okay, so I'm just talking about Anderson localizations. I don't even need to make any conjectures. There's a basis. You have this huge freedom in choice because each of these columns just has to be an eigenvector of the Hamiltonian. but you have this permutation freedom. Okay, so finding this in practice is very hard. But there's one that makes this most diagonal, because all of your eigenstates are just going to look like slightly perturbed versions of your Fock states. And then the most diagonal version of this, so there's the most compressible version, which indeed you can make finite depth while paying, while incurring a finite, or while incurring some vanishing error. Yeah, so. No, you can arbitrarily approximate, you can get to whatever accuracy you want with a finite depth circuit. Yeah, Carlo. That's right. These are also not going to be, these themselves have some decay. They're not going to be arbitrarily long ranged. Yes, you'll end up with a local Hamiltonian written in a locally dressed basis. Okay, good. So for Anderson localization, all of this is exact. If you talk about MBL, this was the existence of this unitary was this L-bit this finite depth unitary was this L-bit picture of MBL that for several years helped us understand many qualitative features of this phase. We've now understood that this is perhaps we know that it's not a complete description. There's more physics happening. So someone asked about higher dimensions. We believe that higher dimensions, MBL is not stable. You can talk about long range interactions. With long range interactions, we believe that MBL is not stable. Even in 1D, there's a whole regime in parameter space where the dynamics can look very, very, very slow. And an experimentalist may never be able to tell whether or not this physics is stable or not, but maybe asymptotically it isn't, okay? But even in those cases, this description should not be thrown out, okay? Because if something gets you 95% of the way there, helps you understand a lot of the observable phenomena, it's useful. I was telling some of you this at that like cookies on the hill. I think the most interesting questions in MBL, I think, are still to be solved. You have this, as David mentioned, there's this broad extended regime. So if I'm talking about 1D, and this is some W over J, maybe there's an MBL phase here. There's a MBL regime. There's an observable crossover, which actually looks quite sharp in numerics and experiments. And there's something unobservable here. Okay, and there's this huge space where we want to understand, and this is thermal, okay, where we want to understand the dynamics, okay, of how the system may ultimately reach thermal equilibrium. And there, there's all of this work on resonances that David mentioned. The Anusha Chandran's group has been doing a lot. I've been involved in some of that. Alan Morningstar, David and I have been working on this, okay? And there, what do resonances do? Okay, resonances are some kind of mixing, very weak mixing between two many-body eigenstates, okay? So it's only two columns. A pairwise resonance is just two columns in this unitary. So it very, very weakly changes the structure of some of the tails of the L-bits. So that structure will keep changing, but it's going to be observable at later and later and later timescales. And eventually, by a mechanism that we don't yet understand, these resonances might interact with this physics of avalanches and ultimately completely destabilize the L-bits. Okay, but this picture of having a locally dressed basis, so in a recent paper by Long, Crowley, myself, and Anusha, we were developing a Jacobi method, which was trying to build in, we were trying to give a description for how thermalization happens through a process of successive resonances. But a starting point for that is a locally dressed basis, which is valid. And then you start modifying this. You see how this flows as you start building in those resonances. Okay, so basically, I'm talking about eigenstate order. I should perhaps call it eigenstate with an asterisk order, okay? Because in cases like Anderson localization, or if I'm really in this MBL phase, these are describing the eigenstates, but in a huge variety of not experimentally relevant regimes, this is not defining the asymptotic eigenstate of the system at infinitely large sizes, but it's defining this locally dressed basis, which is still a useful description of the dynamics, perhaps for all observable timescales. Okay, and the last thing I'll say, I'll re-emphasize, is that even if you're in this regime, there is this very striking signature of this kind of temporal memory across the entire spectrum. Okay, there's no other way that I know of getting something like that. Okay, so I'll move on to Floquet systems right now, and I'll talk about Floquet pre-thermalization. But really, much of what happens there is you're talking about some thermalizing Hamiltonian, which may have order in some small part of the spectrum, but this description of order across the entire spectrum, across all states, that's very special. Yeah. Good. Okay, so the question is, what happens to the non-interacting phase diagram if you add in a small amount of interactions without worrying about all of this stuff? Basically, what we know is, so that was the non-interacting phase diagram where you had spin glass and the paramagnet. Now what we know is that there is, for deep enough in the spin glass phase, you have a localized spin glass. Deep enough in the paramagnet, you have a localized paramagnet. But in this regime where even at the non-interacting critical point, you had this kind of diverging density of states near zero, your single particle wave functions were getting less localized, and your L-bit structure is changing very dramatically, right? It's going from something that looks ZZ-like to something that looks X-like. So actually in this whole sliver here, there is strong numerical and some analytic arguments that this should be thermal. No, because there's really something, I don't believe so, I don't know for a fact, but there really is something very singular happening in the non-interacting problem at this time. And so I believe they'll always, you could get it to close maybe in accessible regimes by making this strong enough, but I believe there'll always be some intervening sliver there. Okay. All right. So I'm going to now switch gears and talk about Floquet systems. Any last questions on this? Yes. Yeah. They don't survive. They thermalize it. Oh, the infinite randomness critical point is actually, in some ways, if you look at the single particle, so there's a paper that I have with Sanjay Mudgalia, David Hughes, and me, where we study the single particle spectrum on this critical line. Even though it's infinite randomness, the properties of the single particle spectrum in terms of how localized those states are as a function of the single particle energy, that's a very special structure, which is less suited to the addition of interactions than deep in the space. So this is more stable here. Yeah. Okay. So now I'm going to switch gear and talk about flow case systems. And I'll give you a very brief review, which I probably wouldn't have needed to do if this was coming at the end of Anusha's lectures, but since it's been 3 packed weeks, I'll do that. Okay, so what is a flow case system? It's time periodic. Okay, so the period is t, and the frequency is 2 pi over t. Even though this Hamiltonian is time dependent, so there's obviously an environment there because you need something to control these couplings. So it's coupled to the environment that changes the couplings in the Hamiltonian. Because the Hamiltonian is time dependent, energy is not conserved. Okay, but I'm going to still treat my dynamics purely unitarily. So your picture should be that there is some environment that's getting coupled with the system to modulate its couplings and is exchanging energy with the system, but it's not getting entangled with the system. Okay, so pure state of the system remains pure in this formalism. Okay, I want to solve the time-dependent Schrodinger equation. Okay, with this time periodic Hamiltonian. And what you know is that these solutions can be written in a form which is very analogous to Bloch's theorem. Okay, so Bloch's theorem tells you the structure of eigenstates when you have a periodic lattice in space. Likewise, you have these Floquet Bloch states. Okay, so you can write any solution in this form, e to the minus I epsilon alpha t, phi alpha of t. Okay, so this is a quasi-energy. And it lives in a Floquet-Brillouin zone because energy is only defined mod omega. Okay, so this is basically from omega minus omega over 2 to omega over 2. You can choose that zero arbitrarily, of course. So energy gets replaced by a quasi-energy defined modulo omega. Anusha talked about multiply driven systems where even more, you have to consider even more of these zones. I'm not going to do that. I'm just going to talk about a single driving frequency. And this is a periodic function. So phi of alpha of t plus t is the same as phi of alpha t. Okay, so okay, now let me look at, I'm gonna define Floquet eigenstates. Okay, alpha, which are going to be which are just psi alpha of 0. Okay, because then if I look at psi alpha of t, that's u of t psi alpha of 0, and that's e to the minus I epsilon alpha t psi alpha of 0 from above, which basically tells you that u of t acting on alpha gives you e to the minus I epsilon alpha t on alpha. Okay, so the set and epsilon alpha, these define, this is the spectrum. I'll write it as e to the I epsilon alpha t. This is the spectrum of u of t, and u of t is the time evolution operator for one period. Okay, so I spent all of this time building up this framework of eigenstates for Hamiltonian systems. As soon as you have some time-dependent problem, the first thought you might have is like, well, now I have this time-dependent problem. I don't have a time-independent Hamiltonian, so I don't have eigenstates. So why did I learn all of this? Or how is any of this going to help me for a time-dependent problem? But at least for flow case systems, there's a very natural and easy answer to that, which is because of this periodicity in time, you have this time evolution operator, which evolves you forward by one period, and you can look at its eigenstates and its eigenvalues, and these tell you everything that you would need for this stroboscopic dynamics. Okay, so this plays, as long as you're probing your dynamics at times t equals nt, the spectrum of this operator controls everything that you need to know. Okay. Questions? So just like you can expand any, this is a complete basis. So just like you can expand any initial state in a basis of your Hamiltonian, you can expand any initial state in a basis of these Floquet eigenstates. And then if you look at the dynamics stroboscopically, so for instance, if I look at T, okay, I should have picked a simpler. Okay, it's basically T, 2T, and so on. This is psi alpha of T, O psi alpha of T. And if I'm looking at a stroboscopic time, this is constant and just given by O alpha alpha. Okay, so certainly if you, this is, yeah. So of course, if you measure, if you just look at some observable like O of T in an eigenstate of the dynamics in a time-independent Hamiltonian, you'll get something constant. Here, if you probe it stroboscopically, you're looking at it in an eigenstate of this U of T, and then again, you get something constant. Okay, good. All right. Okay, so now U of T can be used to formally define a Floquet Hamiltonian. So I can write U of F defines e to the minus I HF T, okay? This is permission, but not unique. Okay, and why is it not unique? Because H Floquet is V dagger D V, where V are the eigenstates of my Floquet unitary. Okay, so these are these eigenstates. But now I have to take a log of this. And because my quasi-energy is only defined mod 2 pi, I only have epsilon 1 up to some P1 omega, P1 is some integer, epsilon 2 plus P2 omega, and so on. Okay, so because I don't know my quasi-energies, I have a great degree of freedom in picking this H Floquet. And indeed, in most many-body problems, this H Floquet is not going to be a sensible Hamiltonian by any stretch. Okay, by the time you take this log and you do these transformations, you may not have any way of making this a sensible local Hamiltonian. Okay, it could be horribly non-local, and more importantly, not just non-local, but also multi-body. Okay, like it could have n-body interactions. So non-local we can handle, but n-body interactions are just totally unphysical. Okay, and generically in a many-body problem, looking at H Floquet will give you that. Okay, good. So you know, this U Floquet again was just e to the minus I dt H of T from 0 to T. Oh, I wanted to write that in the top board. If I take that H Floquet and if I take that expression and I expand it order by order, I can construct H Floquet in a high frequency expansion known as a Magnus expansion. So I take this expression here, which is U Floquet defining an H flow K. I expand it order by order, and what I get is that H flow K can be written as a series, which okay, so HF0 is just the time average, dt H of t. This will define H naught. Okay, so experimentally, a very, very common technique, almost every experimental platform that you've heard about uses this under the hood in some way when they have all their lasers. I'm going to sound like an idiot when they have their lasers going back and forth, but okay. Sorry. No, give me 1 second. I think I have it. I think it's consistent in the next part. Okay, let me just write this out and then I'll do this. Okay. Okay, so the leading order piece is just the time average. The next order piece has two integrals over time. Okay, so two factors of there's a t squared coming from the integrals in time divided by t, so it goes as t, which is order 1 over omega. Okay, and good. So the increasing orders in this expansion have more and more of these nested commutators. Okay, so each of them will be suppressed by an order which is you're right, Leo. I can pull this out. I can make it. I can pull it out and have it be 1 over omega to the n. I just don't know if I consistently define this, but okay. But indeed, it is formally a high frequency expansion, and this expansion is only convergent because you can see that you're getting these H's over omegas coming in. So this expansion is only convergent when some norm of this operator is much less than frequency. But this norm of the operator, this scales like the many-body bandwidth, okay, whereas this is order 1. Okay, so this can never be, so this is not convergent in many-body setting, generically. Okay, but in a single particle problem, you can have the single particle energy scale be comparable. So single particle okay, so single particle, you can have this norm of H of t is some order j quantity, and you can set it up that omega is much bigger than that. Okay, so this brings me to an important point. So let me just talk about single particle for the moment, okay, where I'm not worrying about heating and convergence. So what you can do in a single particle problem is you can talk about you have non-interacting energies. You can make your system translationally invariant. It doesn't matter. You can talk about flow K, block bands, and so on. The point is, in the single particle problem, you can have an H flow K that you can have that expansion be formally convergent, and you can have an H flow K that just looks like the time averaged Hamiltonian, and then has some corrections to it. Okay, so this is extremely useful experimentally to do flow K. When people talk about flow K engineering, this is what they're doing. Your native interactions may have some terms that you don't want. You can do some high frequency drive to average those out to get some desired Hamiltonian. And indeed, this could be an interesting Hamiltonian. It could have some topological properties and so on. But if it's a Hamiltonian that you could get in a static system without any driving, then the flow K engineering is only useful as a tool but it's not giving you any new and interesting physics, okay? So if this is just, if H naught is a valid static Hamiltonian, okay, then no new Floquet physics. Floquet physics. And this is called kind of type 1. So when people talk about type 1 Floquet phases, it's this idea where you're using Floquet engineering to engineer some Hamiltonian that you might be interested in. And in this picture, what you should have in mind is you have some single particle bandwidth, which is order J, and your frequency omega is much bigger than J. So the actual like bands that you get are just normal bands, okay? Type 2 Floquet physics is novel, okay? So it's novel Floquet phases, which are disallowed in static setting. Okay, so formally, this happens when you're driving, to get this kind of physics, you actually need your driving frequency to be the same order as the single particle interactions in your system. So formally, your Magnus expansion is not convergent, but there could be some rotating frame that you could go to in which it is convergent. And it's that frame change that you're doing that's giving you the new physics. Okay, so Magnus convergent in rotating frame. Okay, and how would you tell the difference between these? Let me leave that. Oh, I wrote on this one, it was wet, so it's now stuck. Okay, so one way to see the difference between type 1 and type 2 is to plot, for the non-interacting problem, you can plot what are known as Floquet block bands. Okay, so this is, you fix some time in your problem, say t equals np, and you plot the quasi energies epsilon k. You know, k is an actual, let me work with translationally invariant systems for now. You could have two topologies for your Floquet block bands. In one case, suppose you have k, this is defined between minus pi over a and pi over a. Okay, so that's your actual Brillouin zone. And now you have your Floquet Brillouin zone, which is minus epsilon t to epsilon, or minus pi over t to pi over t. That's epsilon k. So suppose you get some band structure that just looks like that. Okay, so this is a boring band structure that you could have gotten. I mean, it doesn't have to be boring. These could have these could have interesting properties, but this is a band structure that you could easily have gotten in a static system. Okay. On the other hand, so that's type 1. For type 2, the point is that because energy is only defined modulo omega, you could have a band structure which looks like this. So you have minus pi over a to pi over a, and then minus pi over t to pi over t. Okay, but you can see that because energy is only defined mod 2 pi, there's this non-trivial winding in the Floquet-Brillouin zone. This is non-trivial cycle, because by the time you get to the edge of the spatial Brillouin zone, you know you have to come back to the same energy, but now you only have to come back to the same energy mod omega. Okay, so you can get this non-trivial cycle. And this actually gives you, in this case, there's like an average group velocity in the system, which is quantized every period, because you can see there's some there's some chiral motion here. Okay, so this was known as a non-adiabatic Thouless pump, because there's some charge being pumped at every cycle, and there was some beautiful work on this early on in Gil Raphael's group, among others. Yeah. But you don't have a second band. Yes, if I had this, you would be okay, but you don't have that. Sure. Yeah. There's a hand up somewhere. Okay. All right. So the upshot is that, in this case, you have energy which lives on a cylinder. That's the old case. Okay. And then you have some cylinder and momentum space, and you can have some winding like that. But now your energy itself is periodic. So this cylinder becomes a torus. So you have some torus here. And now of your energy levels, you can get some non-trivial winding on this torus. Okay. So to actually classify Floquet phases in this non-interacting setting, you can write down topological invariants just like you would do for normal band theory to classify those systems. But because of this winding in the Floquet-Brillouin zone, you actually need to know what's happening kind of within the period. Okay, you need to know whether there's a non-trivial cycle within the period. And that's the sense in which some of this body of work might be relevant in this newer analysis of Floquet codes and so on, where once again, you need to look at some winding within the period. Okay, so one topological invariant that you can do in this case is you can take your Floquet unitary and you can write it in terms of this micromotion operator. Okay, so this is periodic and has initial conditions, which are the identity. Okay, and now if you want to define some winding number, you actually do an integral over time, kx, ky, for instance, and you'll compute something like phi dagger dt phi dagger dk x phi dk y phi. So basically, the types of topological invariants that you're familiar with computing for just static bands, once you put in this periodicity in time, you also have to take into account this winding in time. And these ideas can be used to kind of generalize these Altman-Zirnbauer classifications of non-interacting systems to the Floquet setting. Okay, I'll end with one very quick example, and then we can either pick up next time with this or just stop there. So there's this beautiful paper by Rudner, Levin, et al. In 2012. As I said, I'm still 10 years, maybe 8 years in the past. Okay. So in their paper, they considered a driven system, which was very simple. Okay. So you have a 2D lattice and you have 4 cycles. So for the first part of the period, you actually have 5 cycles, one in which you do nothing. So for the first part of the period, which is of length t/5, you hop along, this colored block, right? So for the first part of the period, you hop along these bonds, okay? And they make it so you can do an exact swap gate. For the second part, you hop along these bonds. Okay, for the third part, you do this. And for the fourth part, you do that. Okay. So now if your system, if you had a system with periodic boundary conditions and you started somewhere in the bulk of the system, you would go through this complete cycle and come back to yourself. So U of T just looks like the identity with PBCs. So if you were only wanting to study the spectrum of U of T without looking at this micromotion, and you had a system with periodic boundary conditions, this is the most trivial evolution you can get, and you would say there's nothing special, okay? But now, if you cut your system open, what you find is that even though the bulk comes back to itself, you actually have these chiral edge modes. Again, this is Rudner et al., 2012. Okay, so now you get these chiral edge modes, okay? And if you look at the Floquet Brillouin zone here, if you look at the Floquet bands, you see that there's these bulk bands, and then you have the two chiral modes corresponding to the left and right movers on the edges. Okay, so in order to do this, they really needed to make their J comparable to the omega. So JT over 5 is something like over 2 for these different cycles that they were going through. Okay, there's interacting generalizations of this and uses this business of MBL and so on to not heat up your system by Adrian Poe, Ashwin Vishwanath et al. So they did just an interacting version of this and also a version of this on the honeycomb lattice. And indeed, it's that this operator on the edge is like a translation operator. And a translation operator, even though you can get it with this local Floquet dynamics, if you just had a purely 1D system, there was no way to get a translation operator except unless your system is of depth L. Okay, so this Floquet driving has given you a way to realize this kind of non-trivial physics, and pick that up, you really need to look within the entire cycle to see at any given instant, these models look trivial, but if you look at the cycle as a whole, then there's something non-trivial happening. Okay, all right, let me stop there. Well, I'm out of time. Maybe next. I think I prepared a seminar for next for the second half, so I can spend half an hour more and then yeah. Okay. Yeah.
You use
You don't need to use log normal distributions because the question was being asked about positive versus negative, well, about positive means versus zero means. Frequently, people use log normal distributions with some positive J. There's nothing fundamental about it. You don't have to. Because when you look at this infinite, because you're trying to study this, one question that you might be trying to answer is this infinite randomness criticality. And there you know that your couplings flow to these very broad distributions. So you kind of put that in as a starting point and then go from there. That's one reason why they do that. Yeah.
By having energy as limits, like the binding number in one-dimensional system.
Yeah, so exactly. So next time if I decide to do it, I'll talk about the Floquet Ising chain. And one of the things that gives you is a Z2 SPT, where you have kind of some non-trivial charge pumping between the edges. And in a static 1D system, you need Z2 times Z2 to get an SPT phase. Here you don't. So yeah. Okay. Oh yeah.
Besides this way of defining the topological number
Yeah.
on a forest, what is
Time. Yeah.
there's another trick
Right. I believe so. I mean, the question is whether you can also do this in the frequency lattice. I think Anusha spent a lot of time talking about that in her lectures. So yeah, I mean, that's that. It just depends on the problem you're trying to solve, which one might be more illuminating, but both are certainly valid.